I don't, for what it's worth.
Is it amino acid?
Interestingly,
Right. Many of these things have.
so it was very beneficial for...
My name is Matt Caberline, and welcome to the Optispan podcast. All right. Hey, everyone. Look who I ran into at the American Aging Association annual meeting. Kevin White from Prime Health Associates in Oklahoma City. Maybe one of the few, if not the only, longevity doc who actually comes to the science meetings to learn more about the science of aging. So it's great to see you here.
Yeah.
And in fact, we first met at an American Aging Association meeting. So anyways, it's great to be able to reconnect here on site. And I hear that you have some questions for me that have come up since our last opportunity to chat.
Yeah. It is. It always makes me feel like I've dropped a few IQ points whenever I come here to see all these people doing the real science and what's really coming out. And I mean, from a clinician standpoint, it really does make you feel dumb, as you see all this stuff. And maybe that's a harsh word, but it's just, it's kind of overwhelming. But it's very cool to see how it's really coming out. And this is where it starts. And like we talked about before, the information that comes out getting transferred to bedside, it's kind of cool to be here at the cutting edge of where it all really happens.
It's definitely a different world. I mean, from my perspective, spending, 20 plus years doing the kind of research that most people here are talking about in the preclinical world, in the laboratory. It's different in the sense that it's much more sort of discovery based. You're constantly trying to figure out new mechanisms and solve mysteries. But you're also 10, 15 years removed from actually having an impact in the clinic. Whereas, now that I've sort of embarked on this new career at Optispan, I'm much closer to having an impact and actually see the impact that what we're doing has on people's lives. So I think they're both rewarding. Just it's very different approaches and experiences in the two worlds. I wish there were more opportunities for this kind of interaction, and I really hope that in the next 5-10 years we'll start to see conferences where you actually have the scientists interacting with the medical professionals more, because I think that's really where the biggest opportunities are in this field right now.
Yeah. Just having conversations with them. It's a lot different than going to your usual MD clinical, the conversations you have. But it is fun. I think the real scientists enjoy that communication and where I'm coming from and the things we just talked about.
Absolutely. Yeah, absolutely. And I think, as this field is maturing more to that translational component, like the talk we just heard from Adam Salmon on, rapamycin in non-human primates in marmosets, right? I mean, that's really just one step removed from human application. And so I think a lot of the data that come from those kinds of studies, while it doesn't necessarily prove or demonstrate what should be done, what is possible in people, it's getting pretty close. So it's exciting times.
Yeah. Which brings me to my first questions.
All right.
I mean, these are things I thought about. Well, when I came to you and I thought, aren't you tired of talking about rapamycin? And you always said, no, I love talking about it.
Yeah.
At least I think that's what.
No, absolutely. I
feeling.
Yeah, I do love talking about rapamycin.
But one thing, and I've talked to you about rapamycin, and as I try to learn everything about how it works and everything. There's so much intricacies in its mechanism of action. And I told you before, it's like learning all the characters of Lord of the Rings. It's so what I want you to do is, because I'm going to share this with our followers too, is kind of dumb it down for the kids in the room and kind of how it works, and just kind of explain that a bit for starters.
So I will do my best. So you tell me if this is the direction you want to go, because I think there are multiple ways to think about how rapamycin works, right? So first thing that's worth saying is rapamycin is a small molecule, so it's a drug. It is not produced in our bodies. It's actually produced by a bacterium in the soil of Easter Island. That's where the drug gets its name, Rapa Nui. And we don't really know for sure why those bacteria make rapamycin, but the thought is that it helps that particular bacterial species outcompete other microorganisms in the soil, because one of the things that rapamycin is very potent at is slowing how quickly cells divide. And so there are fungal cells in the microbial communities in the soil, and rapamycin is a potent antifungal. So it will basically stop fungal cells from dividing. Which
that was the reason it first came about.
That's the thought, is that's why those bacteria produce it. It's sort of like, biochemical warfare of the microbes, right? Where by producing that molecule, they will slow the division of competing cells in their environment and allow them to win the microbial war. So we don't know for sure, but that's probably why those microbes make rapamycin. There was an excursion to Easter Island, I think this was in the 1960s, that collected soil samples, brought them back to the laboratory, and that's really where rapamycin came from. And it was really first studied based on its ability to slow cell division as either as an antifungal or as an anti-cancer, because of course cancer cells are cells that are dividing too rapidly when they shouldn't, right? That's what makes a cancer a cancer. And so there was a lot of work looking at it as a potential therapeutic for a variety of types of cancers, but nobody really knew how it worked until it was discovered that rapamycin is a specific inhibitor of a protein called mTOR. And they actually named the protein after the drug, mechanistic target of rapamycin. So what is mTOR? So mTOR is really, you can think of it as kind of the key gatekeeper of growth and reproduction at the cellular level. So cells are constantly, and this is true for a single-celled microbe or a complex animal like humans, all of the cells in our body are constantly sensing the surrounding environment and making a series of sort of fundamental decisions based on the environment. And one of those decisions is it a good time to grow and reproduce? And you can think of this at the cellular level, you can think of it at the animal level. At the animal level, if you think about the environment and when is it a good time to have babies? Well, if there's not much food around, that's a really bad time to have babies. And that's essentially what mTOR is sensing. It senses other stuff, primarily senses food or nutrients. And so when nutrients are low, that turns down mTOR and that tells the cell, shut down cell division. When nutrients are high, that turns up mTOR and that tells the cell, go, 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 because there's lots of food to feed your babies. So that's probably the easiest conceptual way to think about mTOR and rapamycin. Rapamycin is a drug that mimics the situation when there's not very much food in the environment, which then causes the cell to shut down growth and reproduction or cell division and become stress resistant. So fundamentally, that's what rapamycin does. There's lots of biochemistry. We know it's a pretty complicated mechanism, but essentially that's how rapamycin works. Now, the one thing that might be worth adding to that, because people will potentially have heard of this, is it turns out there's two flavors of mTOR in the cells. There's mTOR in mTOR complex 1 and mTOR in mTOR complex 2. So the way to think about this is mTOR is a protein and it functions as part of a group of proteins, right? And you could think of it like a group of workers, right, that all have a job to do. So mTOR, it turns out, really has two jobs. One of those jobs it does with one set of other proteins in mTOR complex 1, mTORC1. The other job it does with a different set of proteins in mTOR complex 2. So rapamycin biochemically is a specific inhibitor of mTOR complex 1. Okay, so that's its biochemical activity. The reason this gets confusing is because if you give high doses of rapamycin for a long time, through indirect mechanisms, you can get inhibition of mTOR complex 2. And there's some thought that the beneficial effects of rapamycin, at least for longevity, come from its effects on mTOR complex 1, and some of the side effects, perhaps metabolic or lipid-based side effects, come from inhibition of mTOR complex 2. It's a little bit speculative, but people will hear that if they're kind of in the rapamycin world. So just useful to appreciate those two different roles of mTOR. So I don't know if that's what you were looking for, but that's a primer on rapamycin.
That's good. Yeah, and there's so many other things that have come out that rapamycin improves sound of law enforcement.
Yeah, I don't think we're in trouble.
Keeping
Actually,
Wisconsin
it's
safe.
the fire department.
There's a lot of other benefits that are showing up that we can't really explain yet, or that I can't
For
really quite
rapamycin.
understand. Yeah.
Yeah, so maybe it's useful to talk through what we know. And again, I always try to preface these kinds of conversations by saying it's important to be clear about what we know in laboratory animals and what we know in the real world. Okay. And in the real world, I would say we have data in two places, one in companion dogs living with their owners and the other in humans. So in laboratory animals, and this has been studied in all of the major model organisms used in aging research. So budding yeast, nematode worms, fruit flies, mice, rats. We know that rapamycin treatment can increase lifespan. We know that genetically knocking down mTOR can increase lifespan. So that's important because that reinforces the idea that this is a real and robust effect, that you can do this either with a drug or by genetically knocking down the target of the drug. Okay, so lifespan, rapamycin is the gold standard next to caloric restriction for things that increase lifespan robustly, reproducibly in all of the models that we have to work with. But rapamycin, there's a couple of things that make rapamycin maybe even more appealing as a potential translational intervention than caloric restriction. One being caloric restriction just isn't realistic to get everybody to practice. But we know with rapamycin, you can start the treatment in mice in middle-aged and get essentially the full lifespan benefit. That doesn't seem to be true with caloric restriction. The effects and benefits of caloric restriction seem to be lower when you start in middle age. We also know that rapamycin can either delay functional declines, molecular declines, across many, many different tissues. And I could try to rattle off the list, but it's a long list. So pretty much everywhere people have looked in a mouse, you can see evidence that as that mouse ages, the function goes down in a tissue or organ, and rapamycin seems to preserve that. It may not be true everywhere, but pretty much everywhere people have looked, you can find evidence that rapamycin delays aging or age-related functional decline. And the same thing's true for age-related diseases. So age-related diseases like cancer and kidney disease and heart disease, to the extent mice get those, are delayed or prevented by rapamycin. What's most exciting to me, though, is in at least a few tissues and organs, you can actually see functional rejuvenation in aged animals when you start treatment with rapamycin. That's been shown, I think, most effectively in the oral cavity, where rapamycin can reverse periodontal disease, in the heart, where rapamycin can reverse age-related left ventricular dysfunction, in the immune system, where rapamycin can reverse the decline in the ability of the aged immune system to respond to a vaccine, and in the ovaries, where rapamycin can actually restore ovarian function in mice, female mice that are post-reproductive, at least up to a certain point. So very intriguing, I think, data that rapamycin broadly affects the aging process in addition to increasing lifespan. Okay, so what do we know outside the lab? It's a much smaller, I think, body of data that we have a ton of confidence on. So in dogs, rapamycin there's evidence that it probably can improve age-related declines in heart function, similar to what's been seen in mice. Increases owner-reported activity in 2 different clinical trials. But beyond that, we don't yet know if rapamycin increases lifespan. So that's the goal of the ongoing test of rapamycin in aging dogs clinical trial.
And for the dogs, you're using 1 mg per kg or what?
So we've tested a few doses. We are currently using 0.15 milligram per kilogram given once a week. We've tested 0.1 milligram per kilogram given 3 times a week and 0.05 milligrams per kilogram given 3 times a week. And this timing of dosing is a different question, more complicated or more complication as well. Yeah. In people, most of the people using rapamycin off-label are taking rapamycin once a week. Usually in the 4 to 10 milligram once a week range. Sometimes people take lower than that. But in the clinical use case for organ transplant rejection, most people take rapamycin daily. So the extent to which once weekly is better than daily and has fewer side effects, I think is still a little bit unclear. But the rationale there is that the side effect profile seems to be reduced with once weekly dosing versus daily dosing. The pharmacokinetics are completely different. I really need to do a dedicated episode on the pharmacokinetics of rapamycin, comparing, off-label use once weekly versus what's seen in organ transplant patients, because it's completely different.
Yeah, that's a good point to make.
But what we do know, I think, from the off-label use is there's pretty good evidence that that rapamycin can likely improve vaccine response in healthy older people, at least some healthy older people. There's anecdotal evidence from multiple reports that rapamycin can improve some types of heart disease, hypertrophic cardiomyopathy, dilated cardiomyopathy, a bunch of anecdotal reports of improvements in autoimmune disorders. And I think pretty good evidence that the side effect profile is minimal. So about 15% of people taking it off label seem to get mouth sores.
Yeah.
We did this study on 333 people using rapamycin off label. Mouth sores was the only thing that was
I'm waiting to
statistically
hear.
higher in the rapamycin
I keep
users.
looking for where's the bad news? Where's the bad outcomes?
Yeah, I don't.
What's
I mean,
the downside?
I don't know. Yeah, again, I mean, every drug, every intervention, even exercise has side effects. Undoubtedly, some people experience side effects beyond mouth sores from rapamycin use. We had one dog in one of the trials that developed hypertriglyceridemia, so high triglycerides, but it was really, really high, asymptomatic.
Yeah,
went away when the dog came out of the study, but it's one out of probably 200 now dogs where we've seen that. So pretty rare, we think, in dogs, but that is a known side effect in people. So again, I think there's going to be this individual variation in pharmacokinetics and side effects, and we just don't have a ton of data in the once weekly 4 to 10 milligram range. And the challenge, of course, is that, when you talk about anecdotal stories, you'll get people who tell you all of these great benefits they've had.
Yeah.
Placebo effect is real, but the same thing is true for side effects, right? And that's why, unless you do a clinical trial where you really have it placebo controlled, when people say that they've experienced side effects on rapamycin off label, you also kind of have to say, well, maybe you just had diarrhea that day, because sometimes people have diarrhea. You know what I mean?
Sometimes, yeah, that happens. There's another thing that came up, and I was really interested in this because my genetic profile is high risk for Alzheimer's, right?
ApoE?
No, I mean, my ApoE 3.3 was fine.
Uh-huh.
I mean,
so you have the normal, the most common variants for ApoE, so just polygenic risk.
Yeah. So, which was alarming and made sense with my family history. But I mean, you've heard about the klotho gene and all that, right?
Yeah.
So, and then coming up as a side order of that is that rapamycin actually increases your klotho
Although
release, which is
in mice. I don't know that there's any evidence for that in people, and that would be a super interesting thing to look at. So, so klotho is really interesting. That's an area that I have never done any research on personally, but I certainly have followed that literature. It seems very, very compelling. I don't think the mechanisms are completely understood. There's a really good episode of Peter Attia's podcast with Dina Dubal. I think it's the one that just came out, where she talks about her research on klotho and really does a deep dive into what they know. So yeah, very interesting. And I think she actually mentioned in that podcast that indeed in mice, rapamycin treatment increases levels of circulating klotho.
Yeah.
It'd be really interesting to know if that's true in people. If so, is that part of the mechanism for some of the benefits of rapamycin? The idea being that, the further downstream you can get to the ultimate beneficial effects, you might be able to develop a therapeutic that has fewer side effects and more targeted effects. So maybe klotho, it's a huge assumption, and I actually doubt that it's true, but maybe increasing klotho is everything that rapamycin is doing beneficial. So you could just increase klotho and not have to take rapamycin. Who knows?
Yeah. Well, so yeah, what other questions did I have for you? Oh yeah, can you name the 12 hallmarks of aging?
Okay, let's see. Boy, okay, so DNA damage, telomere shortening, epigenetic dysregulation, mitochondrial dysfunction, of course. Let's see. What have I said so far? Changes in the microbiome. I think they call it dysbiosis. That's 5. Chronic inflammation, 6. Senescence, 7. Loss of proteostasis, 8. Intracellular dysregulation of intracellular communication or something like that.
Alternates,
yeah. Dysregulated nutrient sensing, 10.
Yeah.
Okay, what are the 2 that I've forgotten here? Let me see if I can pull these out of my head. I should be able to.
They're really easy.
Oh, come on, man. What have I forgotten?
You're missing two,
I
right?
know.
You said telomere attrition.
I did. I said DNA damage.
Yeah, genomic instability.
Right. Genomic instability. Right.
Yeah.
DNA damage, subset of genomic instability. Yeah, good point.
Did you say disabled macroautophagy?
Oh, no, of course not. I said proteostasis. And really this one I'm gonna have a little bit of an excuse, which is that macroautophagy is sort of a weird one because macroautophagy impacts proteostasis and mitochondrial dysfunction, right? So this is one that I don't know if it should be its own, but it is. I guess okay, I'll take a hit there. What else did I? And of course, macroautophagy is regulated by mTOR.
I think is that it? Did you have
there's
one
more. What's the last one I missed?
I think I know. Tell me when you're ready. I
said epigenetics. Pretty sure I did.
Epigenetic alterations?
Yeah, pretty sure I said that.
Okay. And you said proteostasis, and you said deregulated nutrient sensing.
I did. Yeah, I got that one.
And you said mitochondrial dysfunction. You said cellular senescence.
I did.
Stem cells.
Oh, stem cells. Yeah. Okay. Yep. Damn it. Well, I don't know if we should include this or not.
Yeah, we should. I'm gonna expose chinks in the armor. Okay. Yep. So 12 hallmarks. What I was going to ask you last night is that name off all the 12 hallmarks and the one thing somebody should do on each one of those. But let's just say forget that because that's a little complicated.
Pick a hallmark.
Let's say pick a hallmark.
I mean, stem cells is a really interesting one. So if you're thinking like, what are the experiments that we're missing, right? So
stem cell exhaustion.
Yeah. So we know with age, at least in complex animals like mammals, that stem cells become less functional, and that could probably contributes to declines in function of many different organs and tissues, especially those that are have a lot of dividing cells. What's a little bit unclear is the extent to which that stem cell dysfunction is a result of intrinsic damage to the stem cell itself, which could be in the form of, genome instability or telomere shortening or, whatever inside the cell, or is it the environment that those stem cells are existing in? And I think it's pretty clear it's both. My intuition or my understanding of the literature to date is that the external environment is maybe more important than the intrinsic damage to the stem cells themselves, at least during normal aging. If we could extend lifespan, if we could double lifespan, it might get to the point where the intrinsic stem cell damage becomes a more problematic feature. But I think given human lifespans now, certainly in mice, it's really the environment the stem cells are in. So if we can change the environment back to a more youthful state, that should allow the stem cells to function more. In fact, I think that's part of what rapamycin and other interventions that reduce chronic inflammation, senolytics, are doing. They're not maybe affecting the stem cells directly, but rapamycin at least, but more likely they're having an impact on stem cell function by knocking down a lot of the chronic inflammation the stem cells are existing in that is impairing their function. Okay, so one of I think the key questions that we've got is, to what extent is stem cell therapy, which would mean taking, young stem cells, just in a very simplistic way, young stem cells, and putting them into an old animal or person, to what extent is that type of a therapy attenuated, the benefits are reduced because you haven't done anything about the old environment. And so there's two things I would say. One is, it hasn't really been convincingly shown reproducibly exactly how you do this in mice, exactly how you can increase lifespan and health span in mice through stem cell therapies. I would really like to see more. There are a couple of papers, but I'd really like to see more data there on what exactly do you do, when do you do it, how often do you have to do these treatments, and how big are the effects. I'm not super convinced you can get large effects from stem cell therapy in mice. I think you can get some benefits in terms of longevity in mice from these therapies. So I would like to see somebody ask the question, if we first rejuvenate the aged system. Maybe that's through parabiosis, maybe that's through rapamycin, maybe it's through fasting, right? Something to knock down chronic inflammation and then do the stem cell therapy. Do you get a much more robust effect? Experimentally, I think that would be really interesting. On the clinical side, I would just like to see a little bit of, regulation and consistency, because right now, nobody really knows what to believe. There are lots of people, probably some people watching this, who've gotten stem cell therapy. Some people swear by it. But the reality is, you go offshore, you have really no idea what's being put in your bodies. There's really no regulation of the quality control and the manufacturing, anything like that. I actually think this is where the regulatory bodies, at least in the United States, have completely dropped the ball, because they've sort of created this Wild West situation where we don't actually know what's being done. And so I think this is actually counterproductive, because nobody knows who to trust, right? Nobody knows what to believe. So you hear about people going to these longevity clinics and getting these treatments, but I'm like, what do I believe? Like, I don't know what they did, So I would really like to see, more rigorously done clinical trials, preferably, in the United States or another country where we have a lot of confidence that the clinical trial infrastructure is robust, so we can actually know what the benefits are. I don't know I'd be interested in your thoughts. I mean, again, I'm not really in the stem cell world, but that's my view from kind of being on the periphery.
Yeah. My own personal, we had one patient, I told you about that went down to Panama, and they seemed like they were pretty dialed in, but he had a good experience, had a good outcome. It was all anecdotal, but
now, when you say pretty dialed in, you mean he was already doing the other stuff that you would want people to do, lifestyle.
Correct.
Yeah.
Yeah. And so he, went down there, and they were pretty rigorous about things they wouldn't allow him to do. And it seemed like it was a pretty organized thing, but I don't know what you're talking about quality control, all that kind of stuff. I just don't know that about their operation down there. So I'd love to see more information on that.
And I mean, a lot of people don't realize this. And look, mistakes happen in hospitals all the time. But I mean, at least we know in the United States, assuming people are following the regulations, and I think most people do, that there are certain manufacturing and clinical standards that you have to hold yourself to when it comes to things that are going to be put inside of the human body. Those standards don't exist in a lot of these places where the pop-up clinics are active right now. And so again, that just worries me, because sure, you would like to think all of these people are, legitimate medical providers. They want to do things to the highest standards. But I mean, we know human nature, right? We know some of these operations are kind of fly by night. They're taking shortcuts. I personally would be really worried about what it is that I'm receiving in one of these sorts of offshore clinics. And again, that's kind of lumping everybody in the same box. I know there are some really good clinics out there.
We should go down to Panama then and have a treatment.
Well, this is what I mean. I don't know that I would want to do that, right?
Yeah. Yeah. Well, I'd go down there and check it out anyway. Yeah. But you said earlier changing the environment for stem cell turnover or reproduction or whatever. What kind of things in the environment would you consider to improve, stem cell exhaustion and everything like that? Can you name off like 3 or 4 things that come to mind?
Yeah, I mean, I think the thing that has the best evidence are like these senescence-associated secretory factors, right? The inflammatory cytokines, some of the inflammatory lipids that are given off by senescent cells that other cells respond to. And so that would be the first place I would look. I'm sure there's other stuff in the aged environment, other peptides and hormones that are changing with aging that are influencing stem cell biology as well. But that's probably the first place I would look is all of the factors that are associated with the increase in the chronic inflammatory state. And this is a good, I think, example again of how the hallmarks of aging are really interconnected in the system, because chronic inflammation is another hallmark of aging, right? And chronic inflammation with age is driven at least in part by dysregulation of the microbiome and by genome instability and by mitochondrial dysfunction. So these things are all connected, but that's where I would look first.
Yeah.
And that's also why I mentioned, and again, maybe people have done this. I've been hammering on the table, this experiment needs to be done for years. That's partly why I mentioned pretreatment with rapamycin, I think is really interesting to think about in the context of stem cell therapy, because we know rapamycin is particularly potent at knocking down these chronic inflammatory signals. So you do a pretreatment with rapamycin, you bring down these chronic inflammatory signals. That's why rapamycin increases vaccine response in the elderly. So you do that, and then you do the stem cell therapy. My hypothesis is, my prediction is, you will get a much more robust response with the stem cells that you're putting into the body, young stem cells, because they're being put into an environment that is closer to the youthful environment rather than the aged environment.
Mm-hmm. Yeah, and chronic inflammation is a cause of continual aging. You have increasing.
Yeah, it certainly goes along with aging, and it very likely, almost certainly plays a causal role in many age-related pathologies.
So what is I'm changing gears here real quick. What's some upcoming research going on right now that you're excited about currently?
Well, that's why I'm here at the meeting, to learn about the latest and greatest research, because I'm not actually doing research anymore. But I will say, I hope that I can get Adam Salmon to sit down with me, because I really would like to talk to him about that marmoset rapamycin study. Marmosets, of course, are non-human primates, so genetically much closer to people. I think when the result comes out, if rapamycin is able to increase lifespan and health span in non-human primates, that will go a long way to many of the non-believers that are still out there, to convincing them that there's a very good chance rapamycin will have a similar effect in people. So I'm hoping I can get Adam to sit down and talk to us about that.
Has there been any other research on it in primates that you're aware of?
Not lifespan. So Adam's study is the only lifespan study. So I'm not sure if this is published yet. I know John, who has also been on the podcast. So John was the person who in my lab showed that we could reverse periodontal disease with rapamycin in mice, has looked in non-human primates. I think it was rhesus monkeys, at short-term effects of rapamycin on oral health in rhesus monkeys, with some interesting data. And he, of course, is now doing the human clinical trial for periodontal disease. I'm not really aware of other studies of rapamycin in non-human primates beyond that. They're probably, at least in the context of aging, I'm sure, when people were first doing the sort of organ transplant research, they had non-human primate studies there, but I'm not aware of anything else in the longevity aging space.
Cool. Well, then that's the first study I'd heard about, lifespan and everything, and actual, a subject that sort of resembles or is closer to the human factor. So
anyway, it's super interesting to see
cool.
Once that data comes out.
So before I let you go, what are you down to? Because you're just the leanest I've ever seen you.
So
this is ridiculous.
It's not ridiculous. It's a goal, right? So so I'm I don't know what my body weight is, but I had a DEXA a week ago, I think, when George Sutton was in town, and he had a DEXA as well. That episode will probably be out before this one. So, and my last DEXA, I was 11 point something. It was like 11.5% body fat. So again, personal goal, touch single digits, and then I'm going to come right back up. So I would like to get to 9.99% body fat, and then come right back up.
It's like you're bobbing for apples and coming back up.
Yeah. And again, this is not meant to suggest that under 10% body fat is the optimal place to be for health. I'm not sure we know. Obviously, that's going to be a very individual kind of thing. I feel great, honestly, at this level. I haven't really felt deprived. I haven't maybe seen a little bit of decline in quality of my workouts in terms of resistance training.
Really?
But yeah, and we didn't really, when George and I went over his DEXAs, we didn't really talk about mine, but also haven't seen any loss of lean mass by DEXAs. So I feel pretty good about the pace at which I've been, changing my body composition, in the sense I've been able to maintain lean mass, lose fat mass. A little bit interesting. I still have probably 0.5 pound of visceral adipose. Again, I'm not super sure how accurate that is with the DEXA, but my visceral adipose hasn't been going down as fast as I would have expected given the loss in overall total body fat. So,
But half a pound.
That's about
all you have in there. That's actually really, really good.
Yeah, I mean, it's good, but I started at like 0.8, I think, or
okay.
It's been bouncing around. So anyways, we'll see. Well, the nice thing is I'm getting DEXAs every 2 to 3 months. So I'll have a nice record of this, self-experiment, and we'll see where we end up.
And strength is notably decreased or somewhat.
I don't think so. So I think if you look at the amount of weight I can lift during my resistance training, it probably hasn't changed much.
Okay.
Hasn't gone up for sure.
Right.
I would say I do have probably more workouts where I feel it's just harder to work up the energy to have a really good workout. Although, since I've been here, the two workouts that I've had here at the conference have been really good. Maybe that's because I've increased my caloric consumption a little bit. I mean, this is all stuff where you're kind of at the margins, right? But again, I think that in terms of the larger trends, like I said, pretty pleased that I haven't seen a loss of lean mass, that, the body fat percentage has come down slowly, but not, I'm probably, I don't know, maybe a pound every 2 weeks loss of total body weight in terms of pace. So really not going very fast.
Yeah.
I don't know. We'll see. We'll see where we end up, but I feel pretty good. And I think I'll get there. I mean, I so far it hasn't gotten to the point where, I feel hungry all the time or anything like that. It probably will, but I guess I should do the math. I probably have 4 or 5 pounds to go. If I can maintain my lean mass, then I'll be there.
Okay. Oh, cool. Well, this has been fun.
What are you at?
Where am I at?
Yeah, your body fat. Your DEXA. When was your last DEXA?
Oh, geez. It was, I was afraid you were going to ask me this.
Because, you know what? I did not want this to become a bro podcast. Sorry. But
it was, I was at 18% like last December.
Yeah. I was at 21 in January 2023.
So I haven't done it again since.
Oh, okay.
So I need to do that as soon as I
do you
get
think
back.
you're down?
I hope so.
Yeah.
I feel like I am, but I don't know. Yeah, we'll see.
All right. Well, you'll have to come back on after you do your next DEXA, or the next time you're in Seattle, we'll get you a DEXA at Optispan.
Yeah.
Awesome. All right.
Thanks,
well, this has been fun. Thanks
thank
for sitting down. And hopefully you all enjoyed that, meander through Rapamycin world into testosterone filled bro podcast world. But anyways, thanks for watching the Optispan podcast. As always, any questions or comments, please place them below. If you are not yet a subscriber, hit that button, and we'll see you next time on the podcast.